So a couple more examples of being able to utilize the closed forms of the summations to be able to find the closed form of a recursive sequence. So we have this arithmetic sequence. Okay, so notice that this is an arithmetic sort of sequence. And what we'd like to do is we'd like to be able to turn it into a closed form. All right. So we know that d sub naught is equal to 3, and then k is greater than or equal to 1. So let's just go through the iterations of this. Now clearly, d sub 0 is 3, easy. The first iteration, that's going to be 4 times the previous instance, which was 3, plus 2. All right. We're going to leave it like that. We're not going to compute it and make it 14. All right. We certainly could, and I'll show you that that's not going to help us one bit in the next iteration. D sub 2, 4 times the previous instance, which is 4 times 3 plus 2, plus 2. Right. Now, if we were to compute that, that's not going to help us any. I think that's going to be 58, because 4 times 14 is 56 plus 2. And notice that we can't see a relationship. So we have 3, 14, 58. There's absolutely no pattern that we can discern immediately from that. That's going to be arithmetic. All right, so unfortunately, can't do anything with that. All right, another way to write D2 would be 4 squared times 3 plus 4 times 2 plus 2, just by distributing the 4. And let's hold on to that, because that might be helpful or it might not. We'll see. D3. 4 times the previous instance, 4 squared times 3, plus 4 times 2 plus 2, plus another 2. Another way to write D3, 4 to the third times 3, plus 4 squared times 2, plus 4 times 2 plus 2. And hopefully we're starting to get a little bit warmer with this. D4. 4 times the previous instance, 4 cubed times 3, plus 4 squared times 2, plus 4 times 2 plus 2, plus another 2. Or, in other words, D4 is 4 to the fourth times 3, plus 4 cubed times 2, plus 4 squared times 2, plus 4 times 2 plus 2. All right. Now, let's just do one more iteration, and hopefully we can discern the pattern from this. D5 is going to be 4 times the previous instance. That's 4 to the fourth times 3, plus 4 cubed times 2, plus 4 squared times 2, plus 4 times 2, plus 2, plus 2. All right. Or, that's going to be 4 to the fifth times 3, plus 4 to the fourth times 2, plus 4 cubed times 2, plus 4 squared times 2, plus 4 times 2 plus 2. All right, now let's try to see some patterns as to what's going on with this. So, looking at the very first term in each of the sequences, each of the first terms has an exponent that matches up to the index. In fact, it's the exponent with a base of 4 each time. And that's sort of a unique term because that's the only one that has a 3 as each of the factors. All the others have a factor of 2 in here. One other thing that we can do to make this a little bit helpful to maybe see a solution is to factor the 2 from each of the terms containing a factor of 2. So one final way we could write D5 would be 4 to the fifth times 3 plus 2 times 4 to the fourth plus 4 cubed plus 4 squared plus 4 plus 1. And that may be very helpful because this might be the sum of the powers of 4. So this is the sum of the fourth powers. Okay. All right, so let's go back up. All right, we kind of know what's going to happen with this guy. This is sort of unique, all right, and it just matches up to the index. So we can just replace that with a variable like n or k. So that might be 4 to the k times 3. All right, we'll hold on to that. But let's see if we can get some sort of closed form for this 4 to the 4th, 4 to the cubed, etc. So, and it looks like right here, that's going to be what we want. So I'm going to go back down. Have that right here. Unfortunately, we notice that unfortunately, it's not the nth power that we have. Because if you notice, the highest power is actually 1 less than the index. Right? So up here, notice that the first factor, or the first term that contains a factor of 2, is 1 less than the index. But that's okay, we can still play around with that and make it work. All right, so here's what we're going to do. We're going to write this into a closed form. So if we were to guess some closed form, let's call this d sub k, okay, or even dn, whatever you want to call it, doesn't matter. We'll use n because that's what the formula uses for the closed form. So d sub n is going to be equal to 4 to the n times 3, and that's just this term right here, that's easy, plus 2 times the closed form, but 1 less than n. So that's going to be 4 to the n plus 1 minus 1 divided by 3. All right? And it's 1 less because we notice that this exponent is 1 less than whatever the index is. Right? We can simplify this, and in fact we are going to simplify this. So that's going to be 3 times 4 to the n plus 2/3 times 4 to the n. Right? So all I did was I just factored out the 3, and then I simplified that 4 to the n plus 1 minus 1, and then minus 2/3. All right, by distributing the 2 and then breaking this up. So these two terms just come from what's inside the parentheses. And then the last thing we can do to make this even cleaner is we can combine our like terms. Notice that we have a 4 to the n, 3 plus 2/3. So I think the most basic form that we can get is we have 9/3 plus 2/3 is 11/3 times 4 to the n minus 2/3. Right? We want to make sure that we have some sort of basic value for this. So the starting value is going to be when n is going to be greater than or equal to 0. And we've checked that because 4 to the 0 is 1. 11/3 minus 2/3 is going to give us 9/3, which is 3. And that was our initial value. And then n is going to be equal to, or the elements of the integers. Okay. So a suggestion might be at this point to pause the video and then to go through and try to work on the next example on your own to make sure that you can do something like that one.